Hey there, everybody. New installment of Dr. Eigenstate Explains. In this one, we're going to be covering something pretty interesting, one that I've wanted to do for a while, but there were some other topics that I wanted to touch on before that. And in this one, we're going to be talking about the Big Bang. Now, before we really jump into what the Big Bang is and what it means, at least to a cosmologist, there's a couple things I want to mention about it. The first one is that the Big Bang, and this might be a hot take for some people, but if you go ask a cosmologist, they'll confirm it. The Big Bang is not the beginning of the universe. I'm going to say that one more time. The Big Bang is not the beginning of the universe. We can go before the Big Bang, and in fact we have, at least theoretically speaking. In terms of observations, we haven't really done that, but theoretically speaking, we can certainly go prior to the Big Bang. I will link an article in the description of this video by PhD theoretical astrophysicist and science communicator, senior science contributor for Forbes magazine, Ethan Siegel, where he mentions this exactly. So if you don't want to take my word for it, this will be an actual PhD theoretical cosmologist telling you this. The second thing that I want to mention about the Big Bang is, it's actually three things. That was the first one. The second one is that the Big Bang is not an event. That is not what the Big Bang is. That's not what it means in cosmology. The Big Bang is a theoretical description that generally involves a series of events that together tell us about the structure and evolution of our universe in the earliest moments that we have been capable of providing physical descriptions for. So the Big Bang is not like this event that happened at some time. It's a series of events that happened, and it's, more importantly, it's the description, the physical description of what happened in the earliest moments of the universe's evolution. So that's the second thing I want to mention. The third thing is that you will rarely hear it. Well, I shouldn't say that. In pop science, you will still hear, and frequently you will still hear the Big Bang or the Big Bang model or the Big Bang theory. But I do want everybody to know that, at least more technically or more formally speaking, it's often referred to as the, and I suppose this would be a good time. Ooh, all sorts of different sizes. I need to stop playing around. Let's get a good size here. It's probably a good time to introduce this. It's often referred to as, well, it would be written, I don't like the way that looks. This symbol here is the Greek letter lambda. The lambda CDM model is what you will often hear it as. The CDM stands for cold, dark matter. Lambda here represents dark energy, which, if you remember from one of my previous videos, installments in this series, dark energy is the currently unknown force that is driving the accelerated expansion rate of the acceleration in the expansion rate of space-time. So this, the lambda CDM model, is essentially the Big Bang model. We've just incorporated both dark energy and dark matter into it, since those both have physical and observable effects on our reality and how it operates. So those are just some preliminary things I wanted to say about the Big Bang before we start jumping into some of the aspects of it and what it is. Number one, the Big Bang is not the beginning of the universe. Number two, the Big Bang is not one event that happened. It's a series of events and the physical descriptions of them. And number three, generally speaking, it's better to refer to it as the lambda CDM model. I also like referring it to as that, not because in my opinion that it's more accurate, but the whole concept of Big Bang tends to put an image in people's heads that's not at all accurate, that there was some sort of explosion or something along those lines, and that's not at all what the Big Bang is, or that it happened at some particular location, which is not at all the case for the Big Bang. There are 5 or 6 different epochs, and that's epoch spelled that way, in the history of the universe that I think really sum up what the Big Bang is and what occurred. And the first one that we're going to start with in this video is often referred to as the electroweak epoch. And it was in this epoch that started at about 10 to the negative 32nd seconds after the Big Bang and lasted until about 10 to the negative 12th seconds after the Big Bang. And during this electroweak epoch, during this period in the universe's evolution, the strong interactions split from what was known as the electroweak interaction, with the electroweak interaction and gravity still essentially being combined into one force. But even though this had happened, I need to clean off the screen there really quick, so ignore the squiggles. The thing is, even though the strong interactions had sort of separated, there was still way too high energy during the electroweak epoch for quarks to really even form. And towards the end of the electroweak epoch, the universe was really just filled with a very hot, very dense quark-gluon plasma, is what it's called. And it's, if you can think of what typical plasma, where you have atomic nuclei and then electrons that are not electrostatically bound to those nuclei. They just have electrons and nuclei sort of existing in a hot soup, quote-unquote, of material. That's what plasma is. Quark-gluon plasma is the same thing, but replace atomic nuclei with quarks and replace electrons with gluons, and it's essentially the same thing. They're not bound together to form stable particles or anything like that, or atomic nuclei or anything of the sort that quarks and gluons tend to make. It is kind of existing in a soup, so to speak, and that's what we call a plasma. But towards the end of the electroweak epoch, electromagnetism and weak interactions did eventually split, and then that swiftly brings us in from the electroweak epoch to the, and you have to remember, these epochs are fractions of seconds long, so I might make it seem like there's a lot going on here, that these occurred over a large period of time. They did not. A lot happened during these very, very small instances of time, these very, very short-lived epochs, but they were very, very short-lived. So in the electroweak epoch, strong interactions split from electroweak in gravity, but couldn't, the force was pretty much null at this point. It couldn't do anything. And then towards the end of right at the end of the electroweak epoch, electromagnetism and weak interactions eventually split. And that, I believe, is generally referred to as electroweak symmetry breaking, where at a low enough energy level, electromagnetism and weak interactions are no longer described as a singular force. They split into separate forces, and if I remember correctly, somebody can correct me in the comments if I'm wrong. I don't think I am, because I rarely am. Ha ha, laugh, laugh. Electroweak symmetry breaking is why the Higgs mechanism occurs, and for those that don't know, the Higgs mechanism is what imparts mass to all elementary particles that have mass. But I'm not going to get too far into that because that will be a different video. So that's the electroweak epoch. The next one, the next epoch, is called the quark epoch. And this lasted from about 10 to the negative 12th to about 10 to the negative 6 seconds after the Big Bang. And during this period, quarks existed, but they couldn't really, like I said, form anything. There was just sort of a hot plasma of quarks, which we're going to represent in white here, and gluons, which we're going to represent in yellow. They weren't bound together to form anything, and some of you might be wondering how that relates to color confinement. If you are asking those kinds of questions, those are good questions to ask. I will get to that in a different video. So they kind of existed here in a plasma. There's nothing bound together, but quarks existed. And it was right at the end of this epoch that the universe had cooled down. The energy level had dropped enough thereby that quarks and gluons could bind together and form hadrons. And that brings us into the next epoch, which, if you haven't guessed what it's called, it is called, let's go back to white. And I apologize for my handwriting. It's never been good, and it's never going to be, so you're going to have to deal with it. The hadron epoch. And during this period, energy had dropped in the universe. It wasn't so energetic. The particle interactions and collisions that were taking place weren't so energetic that they could prevent the formation of hadrons. Hadrons are just composite particles that are comprised of quarks. So like a proton, which is 2 up quarks and 1 down quark, is a hadron. More specifically, it's a baryon, and hadron can be further split into baryons and mesons. But I'm not going to get too far into quantum chromodynamics and things like that, because that will likely come in a different video. During the hadron epoch, the universe, the energy level of the universe dropped enough that hadrons could form. Quarks and gluons could bind together to form hadrons. And so there was sort of a hot soup, again, of hadrons and antihadrons that existed. And as the energy in the universe, it's expanding, the energy continues to drop. What happened is the hadrons and the antihadrons started to annihilate each other, leaving behind only a very, very small amount of hadrons. And since the energy level had dropped, and most of the hadrons had annihilated themselves with the antihadrons, we enter the next era, epoch rather, in the Big Bang, in the earliest moments of the universe's evolution, referred to as the lepton epoch. Leptons are a particular type of subatomic particle. They're a subclassification of fermions, which are particles that are governed by what's called Fermi-Dirac statistics, and they were named after Enrico Fermi. Most people who know about leptons will probably be familiar with the most famous one. We'll all know what it is, the electron. And so during this period in the universe's evolution, number one, I should have mentioned that going into the quark epoch, what had happened with weak interactions is the W and Z bosons began to decay very rapidly, and weak interactions became a very short-range force. That's something I should have mentioned. It just popped in my head. During the lepton epoch, leptons dominated the universe. Things like electrons, muons, tauons, and their antiparticles, and neutrinos as well, since neutrinos are leptons. So it was leptons that dominated the universe during this period. Nothing much interesting happened. Again, just a hot soup of leptons all around, leptons and anti-leptons, and eventually the energy level continued to drop. They started to interact, and particles, antiparticles, matter, antimatter, when it interacts, it annihilates and leaves behind its equivalence of mass in energy. Its mass equivalent in energy. And that's what happened. Most of the leptons and anti-leptons had annihilated, leaving behind only a very small amount of leptons. And this brings us, and this was from about 10 to the negative 6 seconds to about 1 second after the Big Bang. And the fifth one, the fifth, is called fifth epoch. It's called the photon epoch. And it was during this period that light really dominated the universe. There was a lot of light. At the end of the lepton epoch, you had a process that was called neutrino decoupling, where neutrinos, prior to that, the universe was so dense and so energetic that neutrinos actually interacted fairly frequently with other particles. And at the end of the lepton epoch, that stopped, and the neutrinos decoupled, as it's often said, from other forms of matter that existed. And this gives rise to something I don't know if it's ever been observed, but theoretically it certainly should exist, what's often referred to as the cosmic neutrino background, which would have been the neutrinos that we would still be able to detect that were left over from the end of the lepton epoch when they decoupled from the rest of matter. And that will be similar to what the cosmic microwave background is, which I will get to shortly. During the photon epoch, it was mainly light that existed. And this lasted from about 1 second to 10 seconds after the Big Bang. And so you just kind of had photons going around, but generally during this period, photons were just interacting with all the matter. They were consistently being emitted, absorbed, re-emitted, reabsorbed, re-emitted, reabsorbed, all sorts of things. And that's what was going on during the photon epoch. And immediately after, so once 10 seconds had elapsed, roughly, it lasted about 10 seconds, from 1 second to 10 seconds after the Big Bang. Actually, you should say after inflation happened, because what I'm describing is technically the Big Bang. And so after 10 seconds, what happened is Big Bang nucleosynthesis took place, and all these these protons and these electrons that existed, protons red, electrons are blue here, they were able to begin forming stable atoms. Or at least stable nuclei, I should say. The electrons weren't really bound to the atoms yet. I should have said the quarks formed stable hadrons like proton, some neutrons, and then there was electrons and some of their antiparticles, and this kind of existed from about 10 seconds after the Big Bang, let me clean my screen off there, to a whopping 379,000 years after the Big Bang. And this is a magic number. It was after 379,000 years had passed that all these protons existed. I got ahead of myself earlier. And all the little electrons that existed began to form stable, that's not what I was trying to do, stable neutral atoms. And so you would say that, like, here you have a hydrogen atom. One proton, positively charged, one electron, negatively charged. And so because matter was able to begin to form stable, neutral atoms, were able to form, you had hydrogen dominate. There was a little bit of helium and even less lithium that existed during this period. That is often referred to as Big Bang nucleosynthesis. Just the immense energy that existed in the universe, essentially left over from the Big Bang, is what gave rise to the formation of hydrogen, some trace amounts of helium and lithium. And in this process, photons, particles of light, were able to decouple from matter and actually were able to free stream through the vacuum of space without being consistently emitted and absorbed, re-emitted and reabsorbed, and just kind of bouncing off and interacting with all of the electrons and some of the protons that existed prior. And the cool thing is, all those photons that were released can still be detected today. They permeate the entire universe at an almost uniform temperature of 2.73 Kelvin. This is what we call the cosmic microwave background. It is, I'm not going to use the word proof because it's not a word you really see frequently in science, which I know sounds almost paradoxical, but science does not prove things. The cosmic microwave background is definitive observational evidence that the universe was in a very dense, very hot state early on in its evolutionary history. And the reason why is because that it tells us that is because these photons have existed since they decoupled. So prior to that, photons weren't able to free stream through the vacuum of space because of all of the interactions that they were undergoing with all of the various particles that existed at that time. The universe was too hot and too dense for photons to be able to exist without being immediately emitted or absorbed by some other particle, like an electron or a proton, maybe more appropriately quarks inside of protons. But once the universe expanded, whereby it had cooled down enough, those photons could begin free streaming through the vacuum of space. So it wasn't until almost 400,000 years after inflation, after the inflationary epoch, that the first rays of light went zipping across our universe. 400,000 years. That's a long time, actually. Not in the universe's history. It's not, but to us it is. And so to go back to the cosmic neutrino background, it's essentially the same thing. There was a point where the universe cooled down and became less energetic to the point that neutrinos no longer underwent all these interactions with all these other particles and were capable of actually free streaming outward into the vacuum of space. And we at least should be able to detect those neutrinos today, which would make the cosmic neutrino background similar to how we can detect those photons from when they decoupled with matter 379,000 years after inflation to give rise to the cosmic microwave background. We call it the cosmic microwave background because those photons are such low energy now that they appear to us as microwaves. So the period I just got done talking about, by the way, fuck it, I can write it in yellow. is often referred to as recombination. I believe because at one point, I think it was in the Hadron epoch, hadrons actually did form. And I think some of them even very briefly formed atomic nuclei, but they didn't last very long. It's too high energy. And so during recombination, atomic nuclei actually were capable of forming, and atoms were actually capable of forming, so you could say that they recombined to give rise to the simplest elements in the universe, which is why it's called recombination. And that was the period during which, 379,000 years after the Big Bang, that light decoupled from matter, and we can still detect those photons and everything that I just said. So those 6 epochs, I guess you could say, let's write them down here. Jesus. The electroweak epoch, the quark epoch, hadron epoch, lepton epoch, the photon epoch, and then recombination. These 6 periods. Recombination, you can really kind of cut the line off there because the end of the photon epoch was 10 seconds after the Big Bang. So this started at 10 to the negative 32nd seconds after inflation, I should say. This one started 10 to the negative 12th seconds after inflation. This one, I believe, was 10 to the negative 6 seconds after inflation. This one started, I believe, 1 second after inflation, and then this one is 10 seconds. So you could say that from 10 to the negative 32nd seconds after inflation to 10 seconds after inflation is what is generally you can consider recombination a part of this if you want to. I don't think most cosmologists really do, but all of that from 10 to the negative 32nd seconds after inflation to 10 seconds after inflation, all of that, all the things that occurred over that, I mean, quite frankly, it was only about 10 seconds because everything under the 1 second mark were such extremely small amounts of time that you could really just say this all occurred over the course of about 10 seconds. But from 10 to the negative 32nd seconds following inflation to 10 seconds following inflation, all the phenomena that occurred there, the physical descriptions that we have for it, is collectively referred to in the modern age as the Big Bang. The Big Bang originally started as sort of a pejorative against the idea, coined by, I believe it was Fred Hoyle. I almost said Fred Hubble. That's not, don't ask me why. It's Fred Hoyle. I believe it was Fred Hoyle is his name. And the name actually kind of stuck, and so it got called the Big Bang Theory. And I'm not talking about the TV show. For anybody who's been wondering, the TV show has nothing to do with this video, so I'm not explaining that. If you haven't caught on to that by now, I can't help you. But yes, those 5, I mean, if you want, you can throw recombination in there and make it 6 different epochs that form the earliest moments of the universe's evolutionary history are collectively referred to as the Big Bang. I keep referring to inflation in this video, and I'm sure you all are wondering, well, if inflation came before all of this, why didn't you talk about that? I mean, isn't that pretty important? It is. It's quite important. But inflation will be a separate video. Inflation is probably going to be the next video that I do. I wanted to work backward rather than forward. Don't ask me why. That's the way I wanted to do it. If you don't like it, go someplace else. Anyway, the electroweak epoch, the quark epoch, the hadron epoch, the lepton epoch, and the photon epoch, and depending on who you are, you can throw recombination in there as well, collectively make up what we call the Big Bang. It tells us the behavior of the universe, the behavior of things like matter and radiation in the universe, how this all played out, what sorts of things happened. It's the physical model that describes various stages in the earliest moments of the universe's evolutionary history. So to reiterate, We can go prior to these moments. It's called inflation. And I will touch on that, like I said, in the next video. Which means, to reiterate, again, because this is a very, very important point that I desperately, if there's one thing I want you to walk away from this video remembering, it's this. The Big Bang is not the beginning of the universe. The second thing is, the Big Bang is not one event that happened. It's numerous different events, and the amalgamation of the physical models and the observations that we have, which describe all of this that occurred. So just two really, really big points that I want people to walk away knowing. The third one, that you refer to it as the lambda CDM model, call it whatever you want, but I generally refer to it as the lambda CDM model. But the two big things are that the Big Bang is not the beginning of the universe, and the Big Bang is not one event that happened. We can maybe talk about it as if it is, but in reality, it isn't. It's these 5 or 6 different stages, you could say, epochs within the universe's earliest moments of the universe's evolution. And I provided this quote in a previous video, but I think it's a really, really good quote. It comes from the #1 inspiration I have for being interested in physics and doing science education and communication on YouTube and other places amongst the interwebs, and that is from PhD theoretical cosmologist, theoretical physicist, Sean Carroll, and he said, and I might be paraphrasing this, so I apologize if I am more paraphrasing than quoting verbatim, but he said, "The Big Bang is not the beginning of the universe. It is the end of our theoretical understanding of the universe." And this is a sentiment that I have heard a lot of cosmologists talk about. You know, in the pop sci community, you'll often hear physicists, theoretical physicists, cosmologists talk about the beginning of the universe, or that the Big Bang was the beginning of the universe. But in all technicality, they're dumbing it down for the laity who aren't going to understand all of the technicalities. Technically speaking, the Big Bang is not the beginning of the universe, and like I said, I'm going to stress that in this video because it's a very important point. The Big Bang is not the beginning of the universe. It is not one event. We have gone before it, at least theoretically. We don't know. And anybody who watched Sean Carroll on Aaron Ross' channel, I believe that was earlier this week, I want to say, Sean Carroll reiterated frequently, we don't know. And it's the truth. We don't know if the universe has a beginning. We just don't know. There's our physics, the ability for us to describe how our universe behaves and what it's doing, its structure, its function, only takes us back so far in the universe's evolution, in the universe's history. We can't say that that's as far back as anybody could ever go. Maybe it is. It probably isn't, but maybe it is. We just don't know. So when you hear people talk about, well, the Big Bang is the beginning of the universe, we know that the universe had a beginning, they might be arguing philosophically for those, and that's okay, that's a different discussion. But in terms of the science makes absolutely no statements about the beginning of the universe, or whether it even has one, because we don't have physics that can tell us that such is the case. We have physics that can take us back to a certain point, past which we don't know anything, because our physical models are not capable of describing the structure and function of reality at those earliest moments of time. So, at least from the perspective of science, which I would argue is a little bit more important than the philosophy, despite me having a great appreciation for philosophy, I would argue the science is a little bit more important here, because, I mean, describing these things comes down to the physics and the math. You can take that and extend it into philosophy and talk about it, but if you're looking for what is actually going on, you're looking at the physics and you're looking at the math. And according to the physics and the math, you can really, it's sort of a here be monsters kind of place. You can put whatever before this you want, because we don't have physics describing what's before it. It could be monsters, it could be fairies, it could be God, it could be a flying spaghetti monster, it could be a magical unicorn that farted out the universe. We don't know. Nobody knows, because we don't have physics describing it. And that's the thing that I want people to understand. Like I said, the two biggest takeaways from this video for you should be that the Big Bang is not one event, it's the physical descriptions we have of a range of events, a period in the universe's evolution, the earliest moments that we can currently see or understand in the universe's evolution. And secondly, the Big Bang is not the beginning of the universe. So hopefully I drilled those into your head. Hopefully you kind of understand a little bit of the physics that was going on in the early universe with how the forces were operating, what matter was doing, because it's a little bit different. It's very, very exotic. And as always, people, per causam nos profectum, or for the troglodytes who don't know Latin, through reason we progress.